Hi, everybody. So I'm happy to be here. I hope you can all see me over the podium. This is to quote Monty Python now for something completely different. So since I'm the first speaker who's really going to be diving into PFAS, I know a lot of people are thinking about PFAS these days. And I'm going to figure out how to change my slides as well. All right, what's the trick? Is it this one? Maybe.
So maybe you need to put colors.
Now it'll work. Okay, thank you.
Sorry about that.
All right. So we'll start with a quick primer on PFAS for those who may not be too familiar with them. So first of all, whenever you get into this field, it's all acronym soup because you're going to hear all sorts of different acronyms. So just to ground you a little bit, I have some examples up here of sort of the most famous PFAS, and also to tell you a little bit about what the acronyms, how to navigate them. So these are per and polyfluoroalkyl substances. So the perfluorinated ones are the ones where the alkyl chain is completely fluorinated. The polyfluorinated ones still have some carbon-hydrogen bonds available. And so here are three prototypical PFAS. PFOA and PFAS are the two most well-studied and well-known chemicals. So PFOA is what's called a C8 carboxylic acid. PFAS is a C8 sulfonic acid. The main difference between them, aside from the acid head groups, is that the C8 sulfonate has 8 fluorinated carbons. The C7 carboxylate or C8 carboxylate has only 7 perfluorinated carbons, and that tends to affect their properties. So the degree of fluorination matters. And then the 8,2-fluorotelmer alcohol is what's also known as a PFAS precursor. So it has some of those carbon-hydrogen bonds on it, which makes it amenable to partial degradation in the environment. And that means that you can release this and then create the more persistent perfluorinated chemicals as it breaks down. And there are many products that have used these fluorotelmers and other partially fluorinated substances that leads to a lot of transformation and then unknown effects in the environment. The other important things to keep highlighted are the long chain versus the short chain. So we'll talk about the differences in treatability and also in their impacts. Long chain PFAS, there are a few definitions out there, but in general, we're talking about 6 or more fluorinated carbons. So PFHXS, PFHPA and up, and short chains are the shorter ones than that. Transformables are these precursor compounds. There are also a lot of emerging and replacement compounds and trends. So we're moving towards short chain compounds. We're moving towards a lot of use of the ether PFAS. And so here's one that is pretty famous right now, GenX, the ammonium salt of the hexafluoropropylene oxide dimer acid. And these ether compounds were manufactured in order to be more safe than the other PFAS because they thought they would be breaking down in the environment at those ether bonds. Turns out those ether bonds are not very available for transformation, so it's not really happening. So it turns out they're just as persistent as the chemicals they've replaced. And beyond even those usual suspects, the PFAS class is extremely diverse. This was a paper that was recently published in ESNT Letters that kind of lays out a few of these classes if you're interested in understanding what the different groups of PFAS are and just how diverse there are. And members of multiple subgroups are often used in a single product. So one of the things that is responsible for much of the PFAS contamination we see in water systems is the use of this PFAS containing firefighting foam. The aqueous film forming foam is AFFF, and those tend to have complex mixtures of PFAS in them. We only track a handful of these, but as I said, the PFAS universe is very complex. And I think the most, not necessarily surprising, but let's say comprehensive collection of these compounds was recently published this year by Barnabas et al. And it basically pulled together all of the known PFAS definitions, plus what happens if we widen that universe out, because people keep adding more classes to what we consider PFAS. So definition A, you can see, are these alkyl groups that are fluorinated. Definition B is the broadest, and definition C. So whether you have to have hydrogen connected or any compound available. And so if you take you take the broadest definition C and you look at all of the different sources of potential compounds, including patents, the biggest number you get is up to 1.8 million compounds that could belong in the PFAS class. And that's not to say these are all being used, right? We don't really know often what happens to things that are produced in a patent or in a PhD thesis or found somewhere in the grade literature. but it gives us an idea of the structural diversity we may need to start to understand in order to know what's going to happen with all the PFAS compounds that are currently being used. So why is there a concern? PFOA, PFAS, PFNA, Gen X, a handful of other substances have a substantial basis for understanding their toxicity by this point in both humans and wildlife. While there are a wide variety of systems affected by PFAS, there tends to be some concordance between human and animal studies that gives us confidence on what the toxic impacts of many PFAS are. So this is a figure I like to show because I think it gives you a really good grounding on just how diverse the toxic effects of PFAS are, but also where we have the most certainty. This is from a review paper by Sue Fenton et al. And what you can see here is all of these systems that are linked with a solid line are the ones for which we have the highest confidence. And so you can see with high confidence, we understand that many of these PFAS affect thyroid disease, increased cholesterol levels, delayed mammary gland development, reduced response to vaccines, low birth weight, kidney cancer, liver damage, et cetera. And I want to specifically highlight this impact on immune effects, so the reduced response to vaccines. I will caveat this talk by saying that I had to turn it in last Friday. Maybe I turned it on Monday, I'm always late. But it was still before this very recent announcement by the EPA of the new interim health advisory levels for PFOA and PFAS. So in 2016, I believe, the EPA set the first health advisory levels for PFOA and PFAS at 70 parts per trillion, which is a very low number. You know, people who work in analytical chemistry think part per trillion, that's really small, right? We were just talking about milligram per liter levels when we were talking about nitrogen, right? Well, they just revised that level, and for PFOA, the new interim health advisory level is 0.004 parts per trillion, or 4 parts per quadrillion. And that's the level that they think is going to drive the establishment of the MCL. Not to say that that's going to be the MCL, but this is astoundingly low. And that is driven by human observations of immune toxicity in children. So we'll come back to that for a little bit. So how do these PFAS get into our water? I already mentioned one of the ways it happens is through the use of AFFF. Another one, of course, is through industrial activity, and specifically, not surprisingly, the production of fluorochemicals and fluoropolymers. So this is a piece that was published just last week on the 10th on 3M's forever chemical crisis in Europe. So this was a discovery of contamination that had been going on for a long time, but had been sort of under the radar of 3M that led to very high levels of PFAS in the soils. So this plant, I am not going to attempt to pronounce that city, less than a mile from where they were digging a tunnel, you know, as part of a infrastructure development, and they found levels of PFAS in excessive levels in the soil and groundwater in the area. So they had a comment in there about the government is trying to get 3M to remediate the residents' soil, that they would have to dig up 5 feet worth of soil and replace it due to the high levels of PFAS present there. So extensive contamination of soil and water. Here is a picture of a fire training center. So this is in Dutchess County. So this is the state investigating contamination at the fire training center because of the large volume releases of AFFF that are associated with these fire training activities. Of course, military bases and airports are also known to have high levels of PFAS contamination due to the use, again, of this firefighting foam. And the firefighting foam was used not only in fighting fires, but also in all of these training activities, which led to constant and high volume releases of the compounds there. And as a result, there is a substantial contamination of groundwater throughout the US. So this was a paper that was published this year in ES&T that looked at aquifer system well networks to understand the extent of aquifer contamination by PFAS. And they found levels of total PFAS in excess of 100 nanograms per liter in many of these aquifers. And they found that it had to do with distance from training grounds, dissolved organic carbon, percentage of urban land reuse, VOCs, and this the highest relative influence was to the tritium level, which is just telling you what the age of the groundwater is basically. So the newer the groundwater, the more frequent the recharge, the tighter the influence of current activities, the higher the levels of PFAS that are found there. And finally, there is all of these diffuse sources. PFAS are used in food contact materials. They're used in things like makeup. They're used in a lot of cleaning products. And so you get PFAS introduced into the environment through wastewater. And so wastewater treatment has been shown to lead to the release of precursors that are used in a lot of these compounds, which are then transformed during the wastewater treatment process into the more persistent and more mobile acids, which then cannot be any further treated in the wastewater treatment system, and they wind up in the effluent. And of course, from the effluent of one wastewater treatment plant, you often wind up in the influent of your drinking water treatment plant. And so the cycle goes around. For the long chain compounds that are more hydrophobic, during wastewater treatment, they'll wind up in the sludge, and then they can re-enter the environment and cycle through the application of biosolids in land use, which has turned out to be one of the more persistent ways that you can contaminate soils with PFAS. And so this was a study by Tavasoli et al. In 2021, just last year, looking at the signatures of the total concentration of PFAS in the influent and effluent of wastewater treatment systems and the seasonal impact of this. And you can see that the effluent is often higher than the influent due to this transformation of precursor compounds that happens, and that this is higher in the summer where you have higher activity in the biological treatment part of the wastewater treatment plants. And then the final thing that I wanted to mention about how PFAS gets into our water is the you can't escape it route, which is through global atmospheric and ocean cycling. So there's been a number of studies now that have shown high levels of especially the ultra short chain PFAS are now found in rainwater, and that these compounds can undergo long range cycling both through the atmosphere and through oceans. And so basically it means that we are getting global distribution of at least low levels of PFAS. So in other words, PFAS are everywhere. For those of you who have not been following the PFAS crisis, the Environmental Working Group has a really handy map that basically shows all of the known contaminated sites. And I always like to show this map and emphasize, you know, you live in this part that you can't see because it's covered up by dots. And it's not that the states that don't have dots don't have PFAS. It's basically all of the states that have invested in more studies and more monitoring has found more PFAS. So the more you look, the more you find. And basically, we're just waiting to fill in the rest of the map by doing more studies in other places. One thing here that I want to point out as being also important is that there's very few orange dots on this map. These are the other known sites. So in general, there has been water monitoring now under the unregulated contaminant monitoring by the EPA that has led us to understand better which at least public large water systems have PFAS in them. There have been groundwater and well water studies in places where we know there's PFAS contamination due to industrial activity, for example, and many studies done around military sites. But those are by far not the only uses of PFAS. And so we're only beginning to understand now what other industries may lead to PFAS releases. And those will start to actually populate the map with these orange dots as we go forward. And so turning a little bit to what my group has been doing in Pittsburgh, and an example that maybe folks may not have thought about before, I wanted to start, as I get into a little bit of my research, to talk about something that I just stumbled into or someone pulled me into last year. An example that happened in Pittsburgh, it actually happened last July, when they had an incident during, not a residential fire, but a fire at a auto body shop in McKeesport. McKeesport is this small city on the outskirts of Pittsburgh. It's a very poor city, small population. The median household income is less than $30,000. And it's 31% of the population there is in poverty. And they have a history of not great water quality because we live in one of these Rust Belt cities that has had a lot of industrial activity. But what happened there was a fire at an auto body shop. The local firefighters called in for help from the county, and they had a different group come, and somehow they had legacy AFFF on their trucks that they decided to use to help put out this fire. And something happened while they were connecting their equipment to the fire hydrant where they were getting water to fight the fire, that instead of pulling the water out to mix with the AFFF to fight the fire, it sucked the AFFF concentrate into the hydrant and into the drinking water distribution system of this town. And so what resulted is this drinking water advisory that you see here in the map, where they were basically had no access to their water for drinking, bathing, or anything for 3 weeks while they tried to figure out what was going on. And so the local water utility had no experience in PFAS. They had no way to measure PFAS. They had to take samples and send them out to get measured somewhere else. And all the while, people were kind of trying to figure out who's responsible for this. And so they started doing some testing here. This is the PFOA plus PFAS concentration on a log scale in nanograms per liter. And what you see is that this is data that was released by the Water Authority. They looked at several consumers and several residents there, and they also looked at several hydrants. I'll show you that in the next slide. And you can basically see that the levels are kind of all over the place, but a number of them were quite elevated, in that there was a difference between, for a couple of places where they actually did this, the first draw and later draws of the water that they tested, but also that they did this testing between July and August and rarely went back to the same place twice. Take a look at what's going on. And they tested a lot of hydrants because the hydrants is where the problem was. And the line that you see there is the PA proposed threshold for PFOA and PFAS, which now is way above what the EPA just released. So we'll see what happens to that number. So the hydrants are the main target of their sampling. As I said, this was the direct report on the levels in the distribution system. They didn't do any kind of environmental monitoring. And then the way that they solved the problem, which I'll come back to in a minute, is that they flushed the hydrants out into the street. So they basically opened up the hydrants and let them flow out. And then when the water came out clean, they figured they were okay, except that at least one of the hydrants was never able to get clean because the AFFF had been coated the inside of the hydrant and kept shedding PFAS into the water. So eventually I had to remove that hydrant and replace it with a new one. And 6 months later, I was contacted by a group called Women for a Healthy Environment. They're a nonprofit group in the city. And they had been in touch with the community and helped to supply them with some point of use filters. And they wanted to know whether the problem was fixed or not. And so I went there with my grad students and we took a bunch of water samples from the tap water of the residents and looked to see whether we saw anything. And so what you can see here is a distribution of levels of PFAS that range from okay, so 1.8 nanogram per liter up to more than 250 nanogram per liter in one of the houses. So there were at least 2 houses that had greater than 150 nanogram per liter concentrations that were driven mostly by PFAS. And for us, that was clearly the signal from the AFFF. And so this was 6 months after the fire had happened and the drinking water system had been flushed. And in the soil around the fire site, we also took some samples, and the PFAS concentration there was also still 232 nanograms per liter. So what can be said for the surrounding landscape? As I mentioned before, the primary strategy to clear the PFAS contamination distribution system was the flushing of the affected hydrants. And in one case, the hydrant had to be replaced. So the major question we're asking in that area is, where did the flush PFAS go? And clearly it's either in the soils, wherever there were open soils where the water ran off, or it went directly into the Monongahela River, which is just on the edge of that neighborhood. And so into the surrounding surface water in Pittsburgh. And at the same time, the community was worried about what they could do, how they could treat their water. The Water Authority basically told them the problem is solved because we're not seeing PFAS in the hydrants anymore in the distribution system. So the group that I was working with, WHE, passed out these 2-phase water filter point of use filters. These pitcher filters to provide ongoing water treatment after the advisory was lifted. And they decided to use these because it turns out that if you have a filter that is a combination of activated carbon and ion exchange, that seems to be the most effective for what point of use types of filters are available that you can use. And so we actually started collecting some of those filters that have been in place since they were affected, to use them as basically passive samplers to try to understand what's going on there. So the good news is that we now have funding from NIEHS that we're going to go out there and do additional monitoring in the neighborhood. We're going to collect soil samples and try to understand the fate and transport of the PFAS that happened there. And we'll also be providing them with additional filters because my fear is that much like that hydrant that they couldn't fix, these PFAS, especially the long chain PFAS and AFFF, are tending to accumulate in internal deposits in premise plumbing, where they can then continuously shed PFAS into the water over time. And so this is what we're going to be testing in this project and seeing what we can do about it. So sort of good news for this community, because this is a legacy AFFF. Well, it's not good news. So it's bad that it was legacy AFFF. This is the more toxic long chain PFAS, but that does mean that they are more effectively captured by these point of use filters. So there have been studies that show that granular activated carbon is actually pretty good at capturing PFAS and PFOA. So if you look up here, that dark orange dots at the very top that show very little breakthrough, that's PFOS, pretty well captured by your granular activated carbon type systems. That is not the case for your short chain PFAS. If you look at PFHXS and if you look at PFHXA, particularly a kind of lighter orange, that begins to break through much faster. So we have real limitations on how traditional sorbents can remove short chain PFAS from the environment. And in addition, if we're thinking about these very low levels that are being implemented, the biggest cost that has been identified for this, of course, is going to be in regeneration costs, if you can't even regenerate, or replacement costs and disposal costs for all of this sorbent material. And this is what's been shown in studies that were even using not very high regulatory guidelines. So this was based on drinking water regulatory guidelines of 50, 25, or even 10 nanograms per liter. And now we're talking about potentially orders of magnitude lower than that. Those costs are going to become much higher. And again, I made these slides before the new EPA levels were out, but I wanted to point out this wonderful review paper. If you're interested in how these state levels were developed, Gloria Post put all of this information together and collected all of the then, at the time, drinking water guideline levels that were being released by different states. And what I wanted to show is that very clearly, if you start from the very first guidelines that were out in 2000 and follow where the trends are going up to 2020, clearly we're going, on a downwards trend. And if you were to put the new proposed interim health levels from the EPA on this, it would kind of look like the the opposite hockey stick. It would shoot straight down here in 2022. And so we're going to have to figure out how to treat these compounds effectively and cost effectively. And now if we're going to start to add some of the short chain compounds, we're going to get into real challenges. So many of these states are starting to add additional PFAS beyond PFOA and PFAS, and these short chain PFAS are going to be very difficult. So the other thing that we do, we work a lot on in my group is the toxicology of PFAS. And in studying the toxicology of PFAS, we're really interested in their interactions with other molecules. And so in thinking about the challenges of treating short chain PFAS, how we can remove them from water, we know that reverse osmosis can work to some extent, but it's expensive and energy intensive, and it doesn't always work well. And GAC and anion exchange are very, much less effective and require regeneration disposal at large volumes. But we get a clue from understanding the toxicology of PFAS that these short chain compounds, even though they don't bioaccumulate as much, they are still having toxic impacts that indicate they're having interactions with biomolecules. And could we somehow use those interactions to develop new sorbents that could be more effective for short chain PFAS? So that's one thing that we're working on in my group. We're using the properties that make PFAS bioaccumulate or exert toxic impacts to understand their binding to proteins. So we've done work on liver fatty acid binding protein and serum albumin that tend to drive their bioaccumulation potential. And we're also looking at what makes short chain PFAS toxic. So for example, are they having interactions with particular nuclear receptors that drive a lot of their toxic impacts? So we had an initial project that was funded by CERTA to look into whether we can develop proteins as sorbents for PFAS, and whether by tailoring the protein to their interactions specifically to short chain PFAS, we could find better sorbents for these chemicals. And so what we found was we can get better performance than your typical activated carbon for PFHXS, PFHXA, and PFBS using mammalian proteins that are implicated in the toxicity of these compounds. And so we found, for example, that PPAR gamma is at least as good as anion exchange, better than activated carbon for PFAS. And PPAR delta and PPAR alpha seem to bind strongly to some of this short chain PFAS. And so this is kind of interesting because it may give us clues into what sort of sorbents would be good at capturing short chain PFAS. It's probably bad news for toxicity because it means that there are these strong interactions with important nuclear receptors. And then the biggest thing, of course, here is I was just complaining about activated carbon being expensive. Try comparing activated carbon to a purified mammalian protein. It's dirt cheap, right? And so now we're thinking, okay, we have sort of the mechanistic understanding of how this could be harnessed, but we need something a lot cheaper than trying to produce PPAR gamma in the lab. And so we're now kind of taking that understanding and using molecular modeling to screen for potential sorbents. And we're trying to figure out what to screen for that would lead to something that would be cheaper to produce. So we're looking for plant proteins, we're looking for microbial proteins, we're looking at proteins that have generally small molecular weight and simple folding, so that they'd be a lot more amenable to large-scale production in the lab. And so we use a combination of protein database screening and molecular docking simulations to identify these sorbents, and then try to figure out which ones would be the most promising ones. So here's an example of a phospholipase A2 enzyme from rice that we think could be potentially really good. So that line that you see there is sort of a binding above that line, stronger than that line, is likely going to be strong enough to be able to use as a sorbent. And we find that that particular protein should be good for even PFHXA and PFPEA, which are pretty difficult to get out of water. So this is what we're currently working on now with a startup project to look at complementary in vitro methods to evaluate that binding and do some column studies. So stay tuned for what's coming out of that. So in the last couple of minutes, I just wanted to turn to the place we find ourselves in with respect to PFAS. So I'm a scientist. I love doing all this sort of biology and chemistry and engineering stuff together. It's not really going to solve our big problems quickly. And I think that it's really important for us to understand what it means that these new proposed levels are so low. And that is that there's a real need to turn off the PFAS tap. So PFOA and PFAS, we've known are bad actors for a while. The data just keeps going lower and lower in terms of what we think is safe. And as we produce new types of PFAS that were supposed to be, better replacements of these, we find that they're also problematic. And the main problem with these chemicals is that they're extremely persistent. So this is not the chemical you want to release and then 5 years later go, oh, I think we made a mistake, because you're stuck with the stuff you've already put out there unless you spend a ton of money. And so one of the things that I do as part of my less research heavy work is to work with a group of scientists to try to come up with policy instruments, or not an instrument, but a policy frameworks to think about how to move beyond these problems. And I just wanted to point out 2 of them that we think are particularly useful. The first is this concept of essential use, which basically says, we know that PFAS are harmful, we know that they're extremely persistent, so you absolutely should not be using them in things like makeup or surfer shorts, dental floss. Uses that are not critical shouldn't have an extremely persistent, potentially hazardous chemical associated with it. And along with that is the idea that we have too long stuck to this PBT framework to understand chemical hazard assessment, that you need to be both persistent and bioaccumulative and toxic in order to be worth regulating. Because what we found out, for example, with Gen X is that you don't have to be bioaccumulative to exert a toxic effect, right? So that part of it is already out of it. And the second is that we are not omniscient beings, and we won't know necessarily until years down the line that something turns out to be toxic. And so the one thing that is pretty easy to figure out, and that should be a pretty easy design handle to use, is persistence. And while we've known this for a long time, I mean, one of the principles of green chemistry since forever is that you should be working with easily degradable substances. People still seem not to be easily convinced that persistence is bad enough to regulate just on the basis of persistence. And I will also add here, the caveat is that we are talking about synthetic organic chemicals, because we always get people say, oh, sand is persistent, so you can't. No, we're talking about a specific class of chemicals where if we know that persistence is an issue, we know that the exposure and the contamination is highly irreversible. And so we need to be moving away from substances like this, and let's not move to a slightly shorter chain or slightly more branched, also as persistent version when we're thinking about replacements for these compounds. So I tried to not go too much over time, and I'm happy to take questions. And I want to make sure I acknowledge all of my wonderful graduate students, and I look forward to the discussions. Thanks.